Hess's law states that whether a reaction occurs by one or many steps, the overall enthalpy change is the same. So in this example, we can see that adding the given reactions will give us the overall process. If we look at the two given reactions here, we see that this material is a product on one side and a reactant in the second reaction. So just like in mathematics, they can be canceled. Chlorine that occurs on the same side would be added together. Also, HCl gas, which occurs on the same side on the right, would be added together. If we add these two reactions together, these two steps, we get methane, CH4 gas, plus the 2-chlorine, producing CH2Cl2 gas and 2HCl gas. So the two reactions have added together to give us the overall process. Likewise, we add the enthalpies of the two steps, and delta H is negative 202 kilojoules. In the next example, we'll add some other things to this. So we need to use a few principles. First of all, if I were to look at this reaction here, hydrogen plus a half of an oxygen produces water. We see that the enthalpy for this reaction is negative 285.8 kilojoules. If I were to actually multiply through the equation by 2, we see the effect that it has is it exactly doubles the enthalpy as well. Multiplying all the coefficients by 2 has actually caused the enthalpy to be multiplied by 2. If I were to reverse the reaction and write exactly the opposite, water produces hydrogen plus oxygen, then the enthalpy will be the same in magnitude as the first one, and also the sign reverses, so negative would become positive. So if we look at these two, they're related as well. They're opposites, and the coefficients are doubled in this form compared to this one. So if I were to take this enthalpy and multiply by negative 2, then I would get this one. This is the more straightforward of a pair of Hess's law questions that I'll do for you now. This one shows you a strategy that works most of the time, and the next one will be a bit more difficult. So, using a direct approach, we'll look at things that need to be included in the final equation. So this says calculate delta H for the reaction. Methane plus ammonia produces HCN and hydrogen. Everything is in the gas state and it's all balanced. The equations that you're given are N2 gas plus 3H2 gas produce 2NH3 gas. Delta H for this is negative 91.8 kilojoules. Carbon as a solid graphite plus 2H2 gas produce methane gas. Delta H is negative 74.9 kilojoules. And hydrogen gas plus 2 carbon solid graphite and N2 gas produce 2 HCN gas. Delta H is positive 270.3 kilojoules. So what we want to do is look at the final equation we want to achieve, and hopefully we're going to find something that's mentioned only in one of the three equations. I'll number my equations 1, 2, and 3 so you know what I'm referring to. We see that when we look for methane, methane is only included in equation 2. It's only in one place. So this will allow me to figure out what to do with equation 2. I have to move the methane to the opposite side. I have to move it from right to left. In other words, reversing this equation, but the coefficient is fine. So if I take equation 2, and reverse it, you can write ReV, or you can say times negative 1, The negative means you're reversing it, and it's literally what you're doing with the enthalpy here, multiplying it by -1. So CH4 product becomes a reactant. We move it to the left side. And CH4 produces carbon, solid, graphite, plus 2H2 gas, comma, delta H is positive. As we reverse the equation, the negative enthalpy becomes a positive, 74.9 kilojoules. Then I go on and I look at the next substance, ammonia. Similarly, ammonia is mentioned only in equation 1. We see there's no ammonia in equation 2 or 3. Ammonia can only come from equation 1. So I know what to do with equation 1. I need to take equation 1, reverse it, but also to divide all the coefficients by 2. So equation 1 times -1/2. The negative reverses it, and the half adjusts all the coefficients. So the 2NH3 move to the left side and becomes a single NH3 gas. The nitrogen becomes a half of an N2. Fractional coefficients are just fine here because we're just doing math on the equation. And half of the 3 hydrogen will be 3 over 2 H2 gas. Now I do exactly the same thing with my enthalpy. I'm reversing the sign, so this delta H becomes a positive, and half of the 91.8 is 45.9. For my next substance, HCN, luckily for me, is mentioned only in equation 3. It's already on the correct side, but I'm going to need to fix this coefficient. And that's good news. I have all 3 figured out, because the hydrogen would not have been much help here. Hydrogen is in equation 1 and 2 and 3, which means that what I do in one equation would affect another. It's not simple, and it's not very helpful. But I have this telling me what to do with equation 3, so now I know what to do with all 3 equations, and when I add them up, hydrogen should take care of itself, and things that don't appear in the final equation should cancel, because I should have equal and opposite amounts. When I say the hydrogen should take care of itself, what I'm saying is that they should add or subtract, so the net would be 3 on the product side. So my HCN tells me what to do with equation 3. I need to keep it on the same side, but I need half as many. So I'm going to take equation 3, so I'm going to take equation 3 and multiply by 1/2. I have a half a mole of hydrogen, and half of the 2 will be 1 carbon solid graphite, and a half an N2, producing 1 HCN. Delta H will be positive 135.15. So this is 135.2, but we're not going to round off till the end kilojoules. So now we can look for things to cancel. Graphite is on the right-hand side in this equation, 1 mole of graphite and 1 mole of graphite on the left here. They'll cancel. Also, the nitrogen doesn't appear in the final equation, so I'm hoping that will cancel as well. I have a half a mole of nitrogen on the right in this equation. I have a half a mole of nitrogen on the left in this equation. They cancel. So if I look at what's left over and write those down, I have methane on the left, I have ammonia on the left, I have HCN on the right, which I need, but I also have hydrogen in all three equations. So I have 2 hydrogen here, 3 over 2 hydrogen, 1.5 hydrogen here, and a half of a hydrogen on the left side. So my net is 3.5, 3.5 hydrogen on the right hand side, and a half of a hydrogen on the left side. My net is 3 on the right side, just like my final reaction here. So if I write down what's left, I have CH4 plus NH3 produces HCN and 3H2 gas. Delta H, if you follow this method, will be the sum of my individual enthalpies. So it's 74.9 plus 45.9 plus 135.15, and then we round to the least number of decimal places to get our answer. So I get positive 256.0 kilojoules, and I hope you check that and make sure that I got it right. I'm going to try something different in this example. Here I have potassium reacts with chlorine and oxygen to produce potassium chlorate, and I'm given 3 reactions. I'm going to begin as I would normally and number my reactions, 1, 2, and 3. I'm going to look for things that need to be included in the final reaction. So it's an inclusion strategy. And if I look at the first substance, potassium, I see that the potassium can only come from reaction 2. It's on the correct side, and I have the correct number that I need, 1 potassium. When I go on to the next substance in the final reaction, the chlorine, chlorine is also leading me to equation 2. I can find chlorine only in equation 2. So I know that I have the correct number of chlorine on the correct side in equation 2. The oxygen can be found only in equation 3. So that's leading me to know what to do with equation 3. But I'm going to pretend that I don't see the KClO3, that it only exists in equation 1. That would lock me in and tell me exactly what to do. But let's just pretend it's an exam. Under a bit of exam stress, I don't notice that. I'm going to begin the problem with what I do know, and I'm going to simplify it, and then I'm going to look at what remains. So if I begin with equation 2, I know it's unchanged. Equation 2 times 1 means I leave it unchanged. K solid plus 1/2 Cl2 gas produces KCl solid. Delta H is negative 437 kilojoules. Now, when I look at reaction number 3, the oxygen is on the correct side, but I don't have the correct number. In order to get 3/2 oxygen in my final reaction, I need to multiply equation 3 by 3. So I have 3 magnesium plus 3/2 oxygen producing 3 MgO solid. Delta H is negative 1806 kilojoules. Now, if at this point I go back and take another look and I find my potassium chloride, potassium chlorate rather, I know that it needs to move to the other side. The number is correct, but I need to reverse this reaction. I could also look at something that does not appear in the final reaction. So if I look at what I have here now, I have my potassium, my chlorine, I have oxygen, but I also have potassium chloride, and I also have magnesium. In order for these not to appear in the final reaction, they would need to be canceled. So if I were to take the first reaction and reverse it, the first reaction will put 3 magnesium oxide on the left, which can cancel with these. This is kind of a cancellation or elimination strategy. Get rid of the things you don't want by canceling them, by having an equal amount on the opposite side. Reversing this reaction will give me the 3 MgO to cancel with these. It will also bring 3 magnesium to the right to cancel with these, which means that they will not appear in the final reaction. If you had seen the potassium chlorate, then you can also see that we need potassium chlorate to be over here on the right-hand side. Whichever way you figure it out, that's fine. But having more tools in your toolkit gives you more options. So whichever way you figured it out, equation 1 is going to have to be reversed, but the numbers don't need to change. So times -1 means we have potassium chloride on the left and 3 MgO solid, and it produces KClO3 and 3 Mg solid. Delta H will be positive 1852 kilojoules. So now, if I cancel things that are equal and opposite, add things that are in common on the left, add things that are common on the right, I should get the overall reaction that I was looking for. So we can see here that we have 3 magnesium on each side. They can cancel. We have 3 magnesium oxide on each side. They can cancel. And we have potassium chloride on each side, and that can cancel. So what I'm left with is the potassium from this reaction plus 1/2 Cl2 gas plus 3/2 oxygen and it produces, the only thing left on the right side is potassium chloride, KClO3. And all that's left now is to add together the enthalpies. So we have a couple of negative values here and a positive one. So that looks like positive 46 for these two values. So our answer, delta H, will be negative 394, and I need to check that. So after a quick check with the calculator, I was a little bit off of my mental math. It's negative 391 kilojoules. So just to show you, you either try to get the things you need in the final equation or to eliminate the things that you don't need. Good luck with completing your lab. Remember to pay attention to your sig figs. When you're multiplying by exact numbers, the enthalpies will keep their same precision. So if you multiply by 2 or 3 or -2 or cut them in half, whatever, they'll retain the same precision, the same number of decimal places, because you're multiplying by an exact number. When you add the enthalpies together at the end, we keep the same number of decimal places, same precision. Be very, very careful with state. H2O liquid, H2O gas are not the same thing, and they don't have the same enthalpy. So you can't cancel them. You have to have the same material in the same physical state. If you pay attention to all your details, you shouldn't have too much trouble with this. If you do, let your instructor know.